So, in the previous lecture we talked about how elements are synthesized inside the core of a star, and we reached up to that 56 iron region, iron nickel region, where the binding energy per nucleon is highest, and then further fusion is not energetically favorable. But we do have elements much beyond that, all gold and silver and many things beyond that, uranium. So, how these elements are formed, how these nuclei are formed, and then we talk little bit about that, that is the neutron which can sneak into these stable nuclei and make higher and higher isotopes, and from there one can get these bigger, heavier elements. So, today we will discuss the synthesis beyond that iron nickel region, and then maybe we will talk also of some applications. Okay. So, I will go to screen. Okay. So, here is the process. Supposing that neutrons are present, and from where the neutrons are coming, some stray reactions that we talked. Normally reactions proceed through alpha particle capturing, but then there are some stray reactions where once in a while a neutron is produced. So, in the core of the star you do have some neutrons, and at one place if a neutron is produced, maybe after many years, hundreds of years or 50 years, a second neutron will be produced there, because these neutron producing reactions are rare, but neutrons are there. So, look at your screen. Suppose we start with this iron 56 and a neutron just sneaks into it. If that happens, it will make iron 57. Iron 57 is a stable nucleus, it will stay there, and then after many years another neutron comes, and that also goes into this 57 iron, and then it will go to this 58 iron. 58 iron nucleus is also stable and will stay there. Once it is formed, it will stay there, and then again after many years a neutron comes there, is produced there, and that goes into iron 58, and that makes it iron 59. But iron 59 is not a stable nucleus. Now, we have pushed too many neutrons in it, right. The proton number is still 26, but the neutrons, we have pushed too many neutrons, and it is beta active, beta minus active, and it decays. And where will it decay? 59 iron, when it beta minus decays, it will produce 59 cobalt. So, see, from iron we have gone one step ahead in the periodic table, we have gone to cobalt. So, now we have cobalt 59. Now, this cobalt 59 is stable, it will be there for whatever time till a neutron arrives, till a neutron sneaks into it, till a neutron gets absorbed into it and makes cobalt 60. Now, cobalt 60 is once again active, beta active, and this will decay to nickel 60. So, this will decay to nickel 60, it will go from here to here. So, we have gone yet one step ahead in the periodic table. From cobalt we have reached nickel. Then 60 nickel will absorb a neutron and will become 61 nickel. 61 nickel is also stable, this will stay there, and when neutron comes it will become 62 nickel. Then from 62 nickel it will be 63 nickel. So, these slow neutrons, slow means slow in time, neutrons are coming once in a while. So, that is why slow does not mean here that they are moving with low speed. Slow means It's a process is slow, this whole process is very slow. It takes years and years for a fresh neutron to come and get into it. So, 63 nickel, that is beta active, and when it decays, it proton, this neutron, one of the neutrons decay to proton, that will make copper. So, this way the process will go on and you will get elements beyond this iron nickel region. So, this is called slow process or S process, because the time scales involved are decades and centuries. So, this way many of the heavier elements can be formed, and all these elements, as you see, are going at the edge of that beta stability valley, where it is between stable and beta minus active nuclei. But then all the elements of periodic table up to uranium and everything cannot be reached through these S process neutron capture. I will just give you an example. Suppose you have this 110 cadmium. 110 cadmium is a stable nucleus, and then if it absorbs a neutron, it will become 111 cadmium, then 112 cadmium, then 113 cadmium, 114 cadmium and 115 cadmium. This is beta active. This nucleus here, this nucleus is beta active. So, if I go by the process that I described, this will decay to indium, 115 indium. But we do have a stable cadmium isotope 116 cadmium, and that is available on earth, that is available. We do have 116 cadmium nuclei, cadmium isotope. This will not be reached through this S process, because 115 cadmium here is radioactive, it is beta minus active. Before this second neutron, next neutron comes, it will become indium. Similarly, you can see about tin. Tin also, if you start with 118 tin, it will go to 119 tin, 120 tin, and 121 tin is radioactive, beta minus active, already too many neutrons. So, one of the neutrons will decay with a lifetime of 27 hours to this antimony, 121 antimony, but we do have this 122 tin, 124 tin, we do have these isotopes available. So, how these type of things can come? Similarly, here this 122 antimony, this is beta active, it should decay, but then we have on earth we do find this 124 antimony. So, here the process is different, and that process is called rapid process, R process, and that is if there are some events in the star such that a large number of neutrons are produced all of a sudden. So, the neutron flux becomes very heavy. If you have too many neutrons, the time scale of one neutron coming and the next neutron coming, if that time scale becomes so small that a beta decay lifetime is much larger than this time, then it will jump, these beta active particles, right. For example, this 115 cadmium here is beta active with a lifetime of 54 hours. But if neutrons are made available every milliseconds or every microseconds you have neutrons, then before it beta decays, it can absorb another neutron and go to 116 cadmium. Similarly, here from 121 tin, before it decays to antimony, which there the lifetime is 27 hours, if lot many neutrons are available, though one of the neutrons can go into it, making 122 tin, and then 123, and then 124, and so on. In between, if there are some beta active things, they will over the period of time decay, but if there are some stable like this 124 tin stable, then it will be just formed. So, this is known as rapid process or R process. From where this sudden burst of neutron can come? That can come through what we know as, there are many processes possible in stars, and it is a matter of observations and understanding and theoretical modeling and all that. But one important process which is known as supernova process. If you have heavy star, say 10 times, 12 times, 15 times mass of the sun, then once the core becomes iron nickel core, first it will be hydrogen fusion, then helium fusion, carbon fusion, and so on, silicon fusion, then finally it will be iron core. What happens after that? If this mass of the core is large, more than the so called Chandrasekhar limit 1.44 mass of the sun, then the gravitational collapse will continue, because now there is no fusion inside this core, it is already iron. So, the gravitational collapse will take place, and in this gravitational collapse under certain favorable conditions, finally the electrons will combine with protons of those iron nickel nuclei and making neutrons. So, all the protons convert into neutron and it becomes a neutron star, but in the process when these electrons are combining with protons, that time lots of neutrons are made, lot of neutrons are produced, and when it collapses and collapses and collapses, and the outer layers also go towards the center, then these velocities of these outer layers may become very high, some 20% of the speed of light and all that. And then when neutrons become too close to each other, so that Pauli exclusion principle becomes important and they cannot go further towards each other, then this collapse halts, and outer layers are still coming with large velocities, and all of a sudden this collapse stops. So, there is a rebound, the outer layers are coming with high velocities and the core was also going down and everything was collapsing, and the core suddenly stops going down. So, there is a huge impact and shock waves are sent, and all this material, outer layer material, that rebounds. During this process, which may last only few seconds, during this process this huge burst of neutrons that is there, that is produced, that drives this R process, and all these heavy elements which cannot be reached by that slow process S process, that are synthesized. And then from that rebounding outer layers you have explosions, supernova explosions. This is only one process I am telling, there are many more processes. Supernova itself is of various varieties, supernova 1, supernova 2 and so on. I am just describing one process, that too in very brief. So, all this explosion takes place, and this all these heavy elements that are synthesized in the outer layers, all those are thrown off in the space. So, that becomes some kind of a debris, some kind of remains, and that keeps floating in the space, and later on when somewhere in this space these clouds collect and make a new star, then all these heavy elements which are there are already present in whatever proportion they are made, already present there, and this new star will have all these elements. So, that had happened for our solar system too. When sun was created, it is not the first star from the hydrogen helium of Big Bang. Some heavy star had gone through this explosion and there in that heavy star all these heavy elements were synthesized and all those things were thrown in the space, and from that this sun was created. And therefore, in the solar system we have all that carbon and nitrogen and oxygen and everything, iron and platinum and phosphorus and calcium and uranium, all those things that we have in solar system, that has come from these earlier heavy star which has gone through this process. So, that is about formation of elements in star. Everything that we see in this universe, everything that we have on this earth in the solar system, that was at one point of time was created. All these nuclei at one point of time were created inside the star. So, this is known as nucleosynthesis. All right. So, I have almost covered the topics that I wanted to do in this course, starting from the Geiger-Marsden experiment of alpha particle hitting metallic foils, and then interpretation of that by Rutherford, and atomic nucleus or nuclear physics coming into picture. From there 100 years, in 100 years nuclear physics has advanced a lot. We now have lots of understanding of all these processes inside the nucleus, and also it has resulted in many experimental tools which are used by variety of people. So, I will describe some of the 2 or 3 of these experimental tools based on nuclear physics, which are being used by different engineers and scientists and researchers and industry and all that. The first one I would like to do is called Mossbauer Spectroscopy. Mossbauer is a name of a person, Rudolf Mossbauer, who during his PhD work discovered this particular effect, now known as Mossbauer effect, and that has lots and lots of applications, is being used widely for the 60s to this time, some 50 years or so. Rudolf Mossbauer passed away only recently, 14th September 2011. So, this Mossbauer spectroscopy, what is this Mossbauer spectroscopy? Let us consider one nucleus, iron 57. Most of the Mossbauer spectroscopy work is done with this iron 57, that is why I will take that as the example, but there are many more. So, let us look at the ground state and first excited state of iron 57, and that is at 14.4 kilo electron volt. This is the ground state and this is first excited state. The spin is half here and spin is 3/2 here. And when it decays, if iron nucleus is in the first excited state, when it decays to ground state, then it will emit a gamma ray, supposedly 14.4 keV. The next one is at 136 kilo electron volt. That is, this is the energy level of iron 57 nucleus, but we do not have in general isolated iron 57 atom or nucleus. So, we have this iron in some kind of a material. So, if you think of an iron nail or an iron plate, iron door or iron handle, anything of made of iron, as such iron energy levels are different. What are the energy levels of this 57 iron nucleus in say an iron sheet or an iron nail or iron rod? Those energy levels are something of this type. So, this is isolated 57 iron nucleus, and now what we are talking is iron 57 iron in say an iron rod. Normally natural iron, you have almost 98% of that will be 56 Fe and 2% will be 57 Fe, right. So, this is there, we do not have to put it, iron 57 is there in the iron rod. Of course, about 2% of the iron that we have is this one, and almost the remaining thing 98% will be 56 iron. So, what will be the level of this nucleus here? Here the level will be, you will have two levels very close to each other, and then at 14.4 you will have 4 levels. You cannot draw the scale to the drawing to the scale. This difference is still about 14.4 keV, whereas these separations they are of the order of 10 to the power minus 8 eV, electron volts, not keV. And this I equal to half, you have m of I, that is minus half here, and m of I is plus half here. Similarly, here it will be 3 by 2 m of I, this will be 3 by 2, then you will have 1 by 2, then you will have minus 1 by 2, and then you will have minus 3 by 2. When this iron nucleus is part of an iron piece, then this ground state I equal to half, the two substates m I equal to plus half and m I equal to minus half, these will split. And how much is that energy, splitting energy? That will be of the order of 10 to the power minus 8 electron volt, 10 to the power minus 8, 10 nano electron volts. The first excited state is at 14.4 kilo electron volt. The first excited state will also split in 4 parts, m I going from 3 by 2, 1 by 2, minus 1 by 2 and minus 3 by 2, and there also the splitting is about 10 to the power minus 8 electron volt. Why did the nuclear energy levels split? That is because when you have an iron piece, you have ferromagnetic domains, and because of that you have internal magnetic field inside that domain. If you look at one particular iron nucleus, there you have magnetic field coming from ferromagnetic coupling of so many atoms. The electrons overlap, and from there this ferromagnetic coupling takes place, and that creates a lot of magnetic field, and because of that magnetic field these nuclear energy levels split in this particular fashion. If you think of steel, stainless steel also contains iron apart from other things. So, there also you have iron, and 2% of that iron will be 57 iron. So, in that steel environment, steel is not ferromagnetic. In this stainless steel environment, the nuclear energy levels of iron 57, they are changed in a different way, they do not split. If you think of stainless steel, if the isolated energy levels are here, then in stainless steel it will just shift, no splitting, but there will be change, there will be difference. So, this energy difference here and this energy difference here will be different. So, the levels have shifted, the ground state I equal to half had shifted, I equal to 3 by 2, it shifted. So, in this variety, this stainless steel variety, there is no ferromagnetic coupling as such, but still you do have electrons, lots of atoms, and all those atoms have electrons. they are not ferromagnetically coupled, but these electrons interact with the nucleus, and because of that there is shift. That shift is here also, apart from splitting, shift is also there, because the electrons are there, they interact with the nucleus. So, this has both shift as well as split. Here you only have shift. And then if you think of some, let us say, mineral, olivine, pyroxene, or varieties of these compounds, iron compounds, carbonates, and this and that. So, that is another variety. So, let us see, this is FeSiO4, this is olivine. So, there it is the ground state remains the same, and this first excited state that splits. So, energy levels can change because of interaction from that solid in which this iron 57 is embedded. And if I can measure this change in energy level, remember this change is of the order of 10 to the power minus 8 electron volts, and if the gamma rays that is accessible to me, if this is the situation, some gamma ray is emitted, if this is the situation, some gamma ray is emitted. So, what we have in experiments, the thing that we have in experiment are these gamma rays, and gamma ray is the energy difference. So, instead of the pure isolated level difference, instead of that we have slightly less or slightly more energy of gamma rays. Maybe there is a splitting, I have some gamma rays of one energy, some gamma rays of another energy, but the difference is only 10 to the power minus 8 electron volts type. So, in 14.4 kilo electron volt, a difference of 10 to the power minus 8 electron volts, that is say 1 part in 10 to the power 11 or 12. So, with this accuracy, if we can measure these changes, then we can gain insight about that atomic or solid environment around iron 57. If I do not know if some material has come from space, I do not know what it is, but iron is there or some Mossbauer isotope is there, and if we can measure these gamma rays coming from this iron 57, if that is populated and coming from there, then we can come to know whether it is what kind of environment is, what is the kind of s electrons and how much is the overlap of these electrons, or what is the arrangement, cubic or non cubic arrangement, which will split and give me this type of structure, or is there is a ferromagnetic coupling which will give me this type of structure. If there is a ferromagnetic coupling, how strong that ferromagnetic coupling is, all those things we can get about information about that solid at an atomic scale at that level. So, microscopic level we can get information about that solid, and but then the challenge is to measure gamma ray energies with accuracies of 1 part in 10 to the power 12, and Mossbauer spectroscopy is precisely that. The Rudolf Mossbauer, when he discovered this during 57-58 thesis work. So, from there this process, this methodology was developed where we can do that. How do we do that? The process involves some arrangement, experimental arrangement. First I will tell that, and one is that you need a source, what we call source. Source of what? Source is cobalt 57. I am just taking this iron 57 as a prototype for describing what Mossbauer spectroscopy is. It can be done with many other elements also. So, cobalt 57 is a radioactive material. It through internal conversion it decays to iron 57, and when it decays to iron 57, that is created at 136 kV, and from there it decays to that 14.4 kilo electron volt, and from there to the ground state. So, this cobalt 57, this isotope is embedded in a cubic non ferromagnetic material. Most of the time the choice is rhodium, RH. So, cobalt 57 is embedded, it goes and sits at rhodium sites in very dilute proportion, very dilute proportion. So, you have a rhodium, it is a cubic material, crystal structure is cubic, and in that you the manufacturer puts these cobalt 57 nuclei here and there. So, this whole thing becomes a radioactive source which emits gamma rays, and of course, this internal conduction. So, that is there, and after that it is 136 keV gamma rays will come if it goes directly from here to here, and then minus 14, that is 122 keV, those gamma rays will come, and 14.4 keV gamma rays will come. Then our electronics will just pick up that 14.4 keV. So, this is known as source, and in this, because of the interaction of that rhodium solid, the energy levels of iron 57 are shifted, not split, they are just shifted. So, you will get some kind of mono energetic gamma rays of 14.4 keV without splitting. Of course, it will be different from what the energy level difference is in an isolated nucleus. So, gamma ray comes from here. So, I have a source. So, this is, let us say I have a source fixed, cobalt 57 in rhodium, and it is all the time giving me that 14.4 keV gamma rays. Then the material under study, the material for which we want to know the electronic configuration or the arrangement or crystal arrangement, cubic, non-cubic, ferromagnetic, non-ferromagnetic, strength of the coupling, all those things. The solid that we want to study, that solid is placed in front of this, and that is known as absorber. And this solid must contain 57 iron in ground state. Normally, if I take a solid, all the things are in ground state, unless it is a radioactive material. So, iron 57 is already there. We can suppose it is just a iron foil. So, we can just place that iron foil or a steel foil, stainless steel foil, or any material that we want to study. So, make a foil of that or powder it and make a sprinkle that powder somewhere and make some kind of a film or thin palette type of thing. So, that is absorber. So, this is the material which we want to study, which contains this iron 57 in ground state. And then, so the gamma rays are coming here, they are going through this absorber and coming on the other side, and this side we put a detector. Detector for gamma rays, to count these gamma rays, how many gamma rays are coming in a given time. So, that detector is there, the counting system is there, and then the electronics, all that electronics. Apart from this, the source which is mounted on some kind of a stand or something is vibrated. So, you need electronics for this vibration also. This is vibrated to and fro. So, some kind of a oscillatory motion. The maximum velocity generally is few millimeters per second, 10 millimeter per second or so in case of iron, few millimeters per second. So, this is the arrangement. So, how does it work? First, the source has energy levels. This is iron 57 energy levels I am drawing, iron 57 energy levels, ground and 14.4 keV. I am not doing the rest. So, it is giving me some kind of energies, and this energy is, let us say, call it E s, which is, if this energy you call E 1 and this if you call E 2, we would think that this is E 2 minus E 1. There is a catch here, I will talk more about it later, but the gamma ray which is coming is, say, this energy E 2 minus this energy E 1. So, that is coming here. Now, in the absorber you have once again iron 57, and this iron 57 is sitting in the ground state. So, it is here and the first level is here, may be shifted, may be split, not know. So, whatever. So, let us just take a case of simple case of stainless steel variety where it is just shifted. In the source the energy levels are shifted because of this rhodium thing, and there the energy levels are shifted because of this steel, stainless steel environment. So, the shifts will be different, and so this energy is, say, E 1 prime, this energy is E 2 prime, and this difference is E a, and that E a is, let us say, E 2 prime minus E 1 prime, somewhat different, about 10 to the power minus 8 eV. All changes are of that order, 10 to the power minus 8 eV. So, it is slightly different. Now, since we are vibrating it, the gamma rays which are seen by this absorber are coming from a moving source. Sometimes it is going away from the absorber, sometimes it is coming towards the absorber. So, it is Doppler shifted. So, the gamma rays which are coming, they will have this E s 1 plus V by C, this is the energy, and V is variable, we will be changing from V max to minus V max. So, as this source vibrates, as a function of time, its velocity changes because it is in oscillatory motion, and when velocity changes, the energy of the gamma ray that is coming to this absorber, that changes, and it goes from some minimum to some maximum. So, at certain time, this change in energy because of this Doppler shift will make the energy coming from this gamma coming from this source equal to the energy difference which is there. To start with, this E 2 minus E 1 is not the same as E 2 prime minus E 1 prime, because this shift is coming from rhodium environment, this is coming from steel environment. But then when I vibrate this source and change the energy of the gamma ray because of the Doppler effect, because of this shift, at certain point of time this E s 1 plus V by C will become equal to E a if the velocities are proper. And then at that time, and it is a periodic motion. So, in every cycle that will come. So, then there will be a larger probability of this gamma ray getting absorbed in this solid. That is why it is called absorber. If the energy of this gamma ray which is coming to this solid, it is equal to the energy difference which is here, and this iron 57 here it is sitting in the ground state, there will be large probability of absorbing this gamma ray and going to the higher state. After that it will emit its own gamma ray, will come to the ground state, but that emission is in all directions. So, most of it is going in different directions. In this detector, how many gamma rays I am counting as a function of time, and therefore, as a function of velocity. So, what we will find that when the velocities match, this number will go down because gamma rays are getting absorbed here, and for other velocities where the energies are different, the energy of this gamma ray and the energy level difference in this absorber, when they are different, most of the gamma rays will be transmitted and you will have a higher count here. So, if I plot, if this is the velocity and if this is the count as a function of velocity, what I will find at a certain velocity, all of a sudden my counts are less. So, I am having counts like this, these many counts here, here, and all of a sudden I will find that okay, my counts are going down and again it increases. So, number of gamma rays at that particular velocity, this is what we are plotting here, which is coming from that detector. The electronics is there to do all these things and we get this kind of curve, and then from this velocity, at what velocity I am getting this absorption, maximum absorption, I can infer how much was the shift here as compared to this rhodium cobalt source. This is known as Mossbauer spectrum. The shift is because of the interaction of electrons with the nucleus. So, if I know this velocity where dip comes, I know the shift, and from there I infer informations about the electron density inside this nucleus, and especially s electrons, because they overlap with nucleus maximum. Similarly, you can think of a situation, Levin type of situation, Fe SiO4 I told, where the energies are split. So, think of solid in which this first excited state is split in two parts. That happens when the solid is non-ferromagnetic as well as non-cubic. When the crystal structure is non-cubic and there is no ferromagnetic anti-ferromagnetic coupling, it is paramagnetic or diamagnetic, in those kind of situations that first excited state splits in two parts, ground state does not split. So, in that kind of situation you have this is source, these are the energy levels for source E1, E2 you can say, and for absorber you have iron 57 energy levels here and then here. This is I equal to half and this is I equal to 3 by 2. Mi plus minus 3 by 2 are at one place and plus minus half are at different place, which is upper, which is lower, depends on the solid. So, if this is the situation, then this is say E1 prime and here it has split as well as shifted. So, this is let us say E2 prime 1 and E2 prime 2. So, gamma ray is coming with this energy, and here this gamma ray falls on the iron 57 sitting in the ground state and tries to take it either to this level or to this level. It can go from here, it can go here as well as it can go here. So, there are two different energies at which this resonance will take place. If the incoming energy is equal to this much, then also there is a level there and the probability of this gamma ray getting absorbed will increase, and if the energy is equal to this, then also it will increase. So, the gamma ray which is coming from the source, which is Doppler shifted, the energy is Doppler shifted because of this vibration. So, at two different velocities V1 and V2, you will have resonance. V1, when the gamma ray energy after Doppler shift becomes equal to this difference here, and V2 where the gamma ray energy after Doppler shift becomes equal to this one. So, what kind of spectrum it will be there? The spectrum will be something of this sort. You will have all these counts are coming, and then suddenly you find there is this dip, and then again you have more number of counts, and then at some place, some other place, some other velocity, you again find a dip. This is velocity here and this is n here. This is V1 and this is V2. So, this is Mossbauer spectrum. This is when you have normally this is one line single line spectrum. Cubic environment, paramagnetic or diamagnetic. Here it is non-cubic environment, and again paramagnetic, diamagnetic. Substance. And the third is when you have a ferromagnetic or antiferromagnetic coupling in the solid. If you have domains, if the magnetic moments are aligned, in that case, as I said, the levels, the ground state splits in 2 parts and the excited state splits in 4 parts. Iron foil is an example, just a simple iron foil. So, the source, a single line source, E1 here, E2 here, giving me a gamma ray Es equal to E2 minus E1, there is a catch here, and in the absorber you have 2 levels appearing corresponding to the ground state. This is say minus half and this is plus half. I am talking of M of I, and the first excited state is split in 4 parts, and M of I is say minus 3 by 2 here and minus half here and plus half here and plus 3 by 2 here. And this iron nucleus is sitting in the ground state, some of the nuclei in this lower one, some of them in the this plus half state, right. They are all ground state as such. This difference is only 10 to the power minus 8 electron volts. Remember, this difference is 14.4 kilo electron volts. They can go from any of these 2 to any of these 4, obeying what we call selection rules, that delta of M should not exceed 1, the absolute value of delta M, it should not change by more than 1, this way or that way. So, from plus half it cannot go to minus 3 by 2, for example. From plus half it can go to minus half, delta M equal to 1. From plus half it can go to plus half, then from plus half it can go to 3 by 2, right. Delta M is from half, it is going to minus half, change of 1 unit, 0 unit and 1 unit on the other side. Similarly, from minus half it can go to minus 3 by 2, from minus half it can go to minus half, and from minus half it can go to plus half, delta M changing by 1 unit. It cannot go from minus half to plus 3 half, because here it will be changing by 2 units. So, there are 6 possible transitions, and therefore, there are 6 different velocities where absorption will be high, and Mossbauer spectrum, if you look for such a system, that will look something like this. So, at 6 places, so that let us say 1 here, then 2, 3, 4, 5 and 6, you will get 6 line pattern. So, your counts will be distributed around this. So, you will have a 6 line pattern if your system is ferromagnetic or antiferromagnetic. So, these are 6 different velocities where the resonance is taking place, and then by measuring these intensities, by measuring these splittings, these positions, you know about the magnetic properties of the solid. So, you can have different kind of atomic environments. For example, magnetite, you know, in magnetite iron is placed in 2 different kinds of environment. In that crystal structure of magnetite, some of the irons, they are in a particular environment, and others are in some different environments. So, that internal magnetic field is different for this group of iron and that group of iron. So, this group will give its own 6 line pattern and that group will give its own 6 line pattern. So, they will be overlapping. In some cases, you have this 2 line splitting of this type. This is known as quadrupole splitting. So, you can have quadrupole splitting together with the magnetic splitting. So, all combinations are possible. In the solid, if iron is not having just one kind of environment, then each component will give its own Mossbauer spectra and the net result will be a just superposition. So, using computer programs, one can get how many 6 line patterns are there, how many 2 lines patterns are there, how many single line patterns are there, and what are the splitting, what are the intensities of these lines, that the maximum absorption and so on, and from there one can get lots of information about that structure. So, this is being used by chemistry people, this is being used by metallurgists, this is being used by archaeologists, all varieties of people use Mossbauer spectroscopy, which is based on some kind of a nuclear technique to do analysis of their samples. Repeatedly I talked, there is some catch in all this argument that I will be talking in the next lecture.